Good morning, students. In the last lecture, we learned about the graphical representation of a particle performing simple harmonic motion. Today, we are going to discuss another very important topic in this chapter, that is energy in SHM and its conservation. So, what is the energy? We know when a particle performs a linear motion, it possesses potential energy due to its position and kinetic energy due to its motion. So, while we are discussing the energy in the simple harmonic motion, we discuss about the total energy of a particle performing simple harmonic motion. So, first of all, we see what is the potential energy of particle, and then we find the kinetic energy of a particle, and then we know the relation between total energy and this individual energies. That total energy is nothing but the sum of its kinetic energy and potential energy. So first of all, we know that F is equal to minus K multiplied by X, where this K is nothing but a force constant and this X is the displacement, and this force is called as a restoring force acting on a body. We know that this force is oppositely directed to the displacement, so there is a minus sign. But consider for a small displacement dx, the amount of work done dw is equal to minus F multiplied by dx. What is the minus sign indicate here? The minus sign indicate that this work done and this displacement, they are oppositely directed. Okay, so we can find out the total work while the displacement x. So by integrating this equation, or by keeping the value of x is minus kx multiplied by dx, this minus it plus, so it is equal to kx multiplied by dx. So what is this dw? This dw is a small amount of work done to displace a body through amount dx. So to find the total work done, w is equal to integration of kx into dx, which is equal to this k, and what is the integration of x? Dx is equal to x square by 2. So we can write here it is 1 by 2 kx square. Now this work done is stored in the form of potential energy. This work done is stored in the form of potential energy. So we can write here potential energy of a particle performing simple harmonic motion is equal to 1 by 2 k into x square. Okay. Now this is the expression for potential energy. Now we are moving towards the kinetic energy of a particle. But we know that what is the velocity of a particle performing simple harmonic motion? V is equal to, it is omega under root a square minus x square, where this a is the amplitude and x is the displacement, and this omega is nothing but the angular velocity. So if we multiply or we square this equation, this v square is equal to omega square in bracket a square minus x square. Okay, but we know that what is the kinetic energy? The formula for kinetic energy is equal to 1/2 mv square, which is equal to 1 by 2 m this omega square a square minus x square. By replacing this m omega square as a k, so we can write here 1 by 2 k into a square minus x square. So this is the kinetic energy of a particle performing simple harmonic motion. Now we know that the total energy in a simple harmonic motion can be obtained by adding this potential energy and the kinetic energy. So what is the total energy of the simple harmonic motion? This total energy is nothing but potential energy plus the kinetic energy. Okay, so what is potential energy? It is equal to 1 half k into x square plus what is kinetic energy? It is equal to 1 half k into a square minus x square, which is equal to 1 by 2 k into a square. So after solving, we get the total energy of a particle performing simple harmonic motion. So in this way, first of all we find out the potential energy of particle, then we find out the kinetic energy of a particle, and then we add this kinetic energy and potential energy to give the total energy of the particle performing simple harmonic motion. Now there are some cases in which we will see the conservation of energy in the simple harmonic motion. What is the conservation of energy? The conservation of energy state that the total energy remains constant everywhere. Everywhere means at the mean position as well as at the extreme position, or on the other positions the total energy of the particles remains constant. And what is the total energy? The total energy is equal to 1 half Ka square. So we are going to find out the special cases. The first special case is that if at mean position, what happen? At mean position, this x is equal to 0. What? It is equal to 0. If x equal to 0, then what is the potential energy? The potential energy is depend upon the displacement x, and as x equal to 0, we can say that this potential energy equal to 0. And what about the kinetic energy? Kinetic energy is equal to 1 half. If x equal to 0, then we can write it is 1 half Ka square. Therefore the total energy is equal to 1 half Ka square. So this is the total energy at the mean position. Now the second case in which we are taking the particle is at the extreme position. So when it is extreme position, we can say that this x is equal to a, that is the amplitude. The maximum displacement of a particle is equal to the amplitude of a simple harmonic motion. So x is equal to a. If we keep this value in this potential energy equation, we get potential energy is equal to 1 half Ka square, and kinetic energy is equal to, if we keep a is equal to x square, a square is equal to x square, then x square minus x square equal to 0. So this kinetic energy becomes 0. Okay, so if we calculate the total energy in this case, it is equal to 1 half K into a square. So by observing these equations, this is the total energy at mean position, this is the total energy at the extreme position, and this is the total energy at any position. So if we observing the total energy at any position, at mean position, at extreme position, or other than these two positions, the total energy always remains constant, and this constant energy is known as the conservation of energy. Okay, so this can be shown with the help of simple graph which is given in our textbook. So we can draw this diagram, this simple diagram. So this is extreme position, this is mean position, and this is extreme position. Okay, so the graph is like this, and the second graph is like this. So which graph represent which type of energy? So we can take this kinetic energy. This kinetic energy is equal to 0 at the mean position. Sorry, potential energy equal to 0 at the mean position. So this is mean position and this is 0. So this graph represent the potential energy and this graph represent the kinetic energy. And what is this? This is nothing but the total energy. So there are 2 points. There are 2 points and these 2 points represent at which the potential energy and kinetic energy both have same value. Kinetic energy and potential energy both have same value. Okay, so there must be a position at which total energy is equal to kinetic energy plus potential energy having same value. Okay, so in this way we see here the energy, total energy in the simple harmonic motion, as well as we see the conservation of energy in simple harmonic motion. In the next lecture we will see the another property of simple harmonic motion, or we are going to see the examples in simple harmonic motion. So this is enough for today. Have a good day. Bye.